Okay, hey, welcome back, class. Today we're going to start a new topic called nuclear chemistry. And over the next probably 2 weeks, roughly, we are going to be talking about stuff like what is nuclear chemistry, types of nuclear decay, fission versus fusion, and how to balance nuclear equations. So, in saying that, let's kind of jump into where we're going today. In order to do that, you first need to know what objectives. So we need to map out where we're going. So the first one is to identify the two different ways to write nuclides. Okay, you'll learn about that in a second. Next thing I want you to be able to do by the end of the day is to explain the laws of conservation of mass and conservation of energy. And finally, we need to determine how protons and neutrons relate to the stability of an atom overall. So in saying that, let's dive into nuclear chemistry. So some terminology before we even get going into this. We're going to throw some new words at you, and we don't want you to get confused here. So let's talk about these new words. A nucleus we know is made up of protons and neutrons. Okay, so the nucleus contains protons and neutrons. This collection is also called a nucleon. Okay, so nucleon you can think of as the protons and neutrons all together, while the nuclide is referring to an atom as its whole. Okay, so nucleon and nuclide. Nucleon, just basically the stuff within the nucleus. Nuclide is the whole atom. So how do we write and identify nuclides, and how do we write nuclear atoms? So this is extremely similar, if not like exactly the same as writing your normal isotopes. So as we see, we got radium, we got two ways. We got it with the chemical symbol as one, and then we also got it written out. Okay, if it's written out all the way, we understand that the number after it, that's going to be the atomic mass or the mass number of that element. Well, if it's written out like our radium Ra with 228 and 88. Our 228, the top number, is always going to be your mass number, while your bottom number is always going to be your atomic number. Now, hint, hint. Whenever we're talking atomic number and stuff, remember, the atomic number is the same as the number of protons. So keep that in mind. Now that you've learned what nuclide is, a nucleon is, and you learn how to write nuclear isotopes, now let's talk about conservation laws. So conservation laws tell us how matter and energy interact within a closed system. So what do I mean by a closed system? I mean that there are no outside factors affecting it. Meaning like, okay, if we put the reaction in a chamber and did not allow air or anything else to mess with it, that would be a closed system. There's no other components that are going to mess with that reaction. So the law of conservation of mass is the first one we talk about. It says mass cannot be created or destroyed within a closed system, meaning what I start with theoretically should be what I end with. Okay, if I have a chemical reaction, how much I start with and how much I end with should be the same. Okay, again, with a closed system. What about the law of conservation of energy? Well, it's the same thing as law of conservation of mass, but with energy. The energy cannot be created or destroyed in a closed system, meaning I can't make more energy. That energy has to originate from somewhere. Okay, the energy that I had to start a reaction will be ultimately is all accounted for in the energy at the end of the reaction. Now it might be displaced in different forms, but either way it's still the same amount of energy. So that brings the question, why is the mass of an atom less than the sum of all of its parts? Well, what do you mean, Mr. Kaufman? If mass is conserved, then the atom, all the mass in there, all those little subatomic particles coming together, should equal the amount of mass within the total element. Well, let's look at helium, for example. Helium has two protons. Those two protons each weigh 1.007276 atomic mass units, or AMUs. Okay? If we multiply that by 2, so 1 for each proton, we get a total of 2.014552. Hold on to that number. So that's the protons. Let's go to the neutrons. Well, each neutron weighs 1.008665. So we have 2 neutrons in a helium atom, because remember, helium is atomic mass and it has 2 protons. So if we have the atomic mass minus proton, that's 2 neutrons. So we multiply that 1.00 such and such by 2, and we're going to get 2.017330. Okay, so that's 2 numbers we're going to hold on to. Yes, we're going to go in depth here. Now, if we add our electrons, okay, helium is neutral. So our helium atom is, if it has 2 protons, it has 2 electrons. So each one of those electrons are going to weigh 0.0005486. If we multiply that by 2 for its 2 electrons, we get 0.001097. Okay, so we take all the numbers for our protons, neutrons, and electrons, we add them together, and we get a number something like 4.032976. Big whoop. Okay, but if we look at our atomic mass or our weighed out mass for helium, it's actually 4.002602. Well, that's different than our number that we calculated out with everything added together. Why is there a deficit of 0.030377 atomic mass units? If mass is conserved and energy is conserved, whenever I take all of these subatomic particles to put them together, why is there less than when I started with them? Well, the answer to that goes back to Albert Einstein's famous equation, E equals mc squared. So if mass and energy are related in this, so E, energy, and then M, and then M is mass. So we can see we have an equation with mass and energy in it. If mass and energy are related, then it's safe to assume that mass and energy can be converted to each other. So in other words, they can be interchanged. When a nucleus is formed from a nucleon, the energy released, or the loss of mass that we're seeing, is called the nuclear binding energy. Okay, so let's back up a second. We noticed that when we had added all of our subatomic particles together, the weights of them all, we had a mass deficit. Okay, Albert Einstein's equation, E equals mc squared, shows us there's a relation between energy and mass. So what happened was that depletion in mass was actually accounted for in the increase of energy. Okay, so this loss of mass to release energy is what we call our nuclear binding energy. Now we're going to talk a lot about this in a second, as far as everything that we're going to be talking about is dealing with our nuclear binding energy, how stable an atom is going to be, how much energy is holding it together. Okay, so just bear with me and let's keep going. So why is binding energy important? Well, binding energy is used to compare the stability of a nucleus. Okay, we can say, hey, the binding energy released by atom X is greater than atom Y. Well, because it released binding energy, that's going to mean that that atom is going to be more tightly bound. So the higher the binding energy per nucleon, or per nucleus, the more tight the nucleus is held together. In other words, the more stable it is. So a higher binding energy equals a more stable atom. So stability of an atom. So nuclear chemistry and dealing with stability. The big thing we've realized with an atom is in the nucleus, and in nuclear chemistry we're talking about the nucleus. Protons and neutrons are inside that nucleus. We've talked about that. Now, the number of protons and number of neutrons help determine the stability of an atom. You've heard the saying opposites attract, and that comes from science saying that opposite charges are going to attract each other, while like charges are going to repel each other. So if we have a whole bunch of protons in a nucleus and we don't have any neutrons in there, those positively charged particles are going to not want to bind to each other. They're going to want to repel each other. But because we have neutrons in there between the protons, that allows the nucleus to bind together and hold itself together. Chemists have done many experiments and collected some precise data and determined there is a relationship between the stability of a nucleus and the number of protons and neutrons within that nucleus. They've done a graph that kind of looks like what is shown on the slide now. And if the ratio of neutrons to protons falls within a certain range, they have found that that atom is likely to be stable. So they have found the top end and the bottom end. So let's go into that and let's talk about that. What we're talking about here is the band of stability. If a ratio falls or a number falls in between these ratios, it is going to be considered stable. If the ratio of neutrons to protons is greater than 1 to 1, then it's going to be considered stable. So that's the low end. But the high end, if it's less than or equal to 1.5 to 1, then it's going to be stable. So anything above 1.5 and 1 is going to be unstable, and anything below 1 to 1 is unstable. Before we get into practice problems, so why is this important? Why is this a thing? Why is the band of stability a deal in chemistry? Well, this trend explains the electrostatic forces between protons in the nucleus. So we talked about the protons are going to be repulsed by each other. Okay, you have protons in there; they're going to be repulsed by each other. That's why we need that's why we need neutrons in there to kind of space them out a bit, so that those protons aren't trying to completely repel each other. Well, let's think about this. If our atomic number increases, that's going to also increase the number of protons in our nucleus. So the more protons we get into that nucleus, the more repulsive charges there is going to be. So we're going to need more neutrons to counteract that. That's where we get to the point where we have the ratio of 1.5 neutrons to every 1 proton is stable. Or the idea of the band of stability is to have a way in which we know numerically, we can figure out, okay, this atom is stable, okay, because it has X amount of protons to X amount of neutrons. Okay, and if it falls within that ratio, we're good. So now we get to do some practice, putting this into practice. Determine if the following nuclide is stable or not. Okay, so the first one is helium, 4,2 helium. So we see that its atomic mass is 4. Okay, that means it had the protons plus neutrons equal the atomic mass. If it has 2 protons, that's what it's saying there, then that must mean it has 2 neutrons. So it has a 2 protons to 2 neutron ratio, which can be reduced down to 1 to 1. Okay, so we have for every proton we have a neutron, and that means it's a stable helium. 4,2 helium is a stable isotope. So our next one is lead 20682. So if we take this out, first of all, we got to figure out how many neutrons it has. We know its atomic mass is 206. So we take our 206 and we minus our 82 from it to get our neutrons. That's 124 neutrons. Now, that means we have 124 neutrons to 82 protons. If we do that ratio out, we get, or reduce that down, we get roughly 1.51 to neutrons to 1 proton. Okay, so that's on the top end of our ratio. That's above the 1.5 that is our top end of our ratio. So that means this is actually a very unstable atom, and it's probably going to switch up to its more stable form. Our last one is 3416 sulfur. So what we're going to do is take our atomic mass, which is 34, minus our 16, which is the number of protons. That's going to give us 18 neutrons. So we have 18 neutrons to 16 protons. So if we divide that out, we take our 18, our number of neutrons, divided by our number of protons, which is 16, we get 1.2 or 1.125. Okay, that is above a ratio of 1.1 to 1, and is also below a ratio of 1.5 to 1. So that means that it's in that band of stability, which means that this sulfur isotope is stable. Okay, so I hope this kind of helped you out. I know it's a complicated topic, and I know it's hard, but I hope this video kind of gave you some new understanding of some nuclear chemistry. On our next one, we're going to talk about the different types of nuclear decay. So hold on, you got this. Otherwise, keep up the good work and see you next time.